Hello, welcome to the class on E540 Advanced Electromagnetic Theory and Antennas. I am Professor Rakesh Singh Chattermayam. So in this class we'll discuss about aperture antennas. So in the previous classes we have discussed about the antennas which are called type 1 antennas. Type 1 antennas we consider the actual source. Antenna is the actual source for the radiation, such as dipole antenna, loop antennas. So the current flowing in the dipole and loop antenna was a source for the radiation. So we call those kind of antenna as type 1 antennas. So in this class what we are going to study is called type 2 antennas, in which the source is somewhere else and we actually find the equivalent source from the field radiated from the original source and use that equivalent source for finding the fields of the aperture antennas. So all these things will be very clear after we study this class. So here in the type 2 antennas we use equivalent source for radiation. So in the antenna analysis for type 1 antennas, what we did was we first find the potentials from the current densities. We find magnetic vector potential from the electric current density, and we find the electric potential from the magnetic current density, and find the electric field and magnetic fields. That was the procedure. So now for the type 2 antennas we need to have one more extra step here. First, what we need to do is we need to know the fields which are there in the aperture. So what are the fields in the aperture? Once you have that, you can find the equivalent source, magnetic current density and electric current density, then find the magnetic vector potential and electric vector potential, and find the fields. So we have one extra step here. We need to know the aperture fields first. So let us look at this structure. We have a conductor. This structure is a conductor. Usually it's infinite in extent, but for drawing, easier drawing, I have just shown as a rectangle. So it will be extending infinitely in the xy plane. It's a conductor. In that, at the origin you have a source, you have a slot. You have cut out some portion of the conductor, and that slot is the aperture. So conductors are everywhere in the xy plane, and at the origin you have a circular aperture here, and this aperture is the source for radiation. So point to be noted, we are placing this conductor in the xy plane, and aperture is also in the xy plane. In this case aperture is circular in shape, and you have, see, basically this is a source. Now equivalent source will be found out from this aperture. So now the variable for the source is with a prime coordinates. So r dash is the location of any arbitrary source here at position at p dash, and you can consider ds dash. This is a circular, that's a area element for the source. The distance of the source and the observation point will be r1. Distance of the origin to the observation point p would be r. So r is the vector from origin to the observation point. R1 is a vector from the source to the observation point, and in this particular case aperture is positioned in the xy plane. So in such kind of structures we actually know the aperture field beforehand. So aperture field is usually given to you. For example, you have an open-ended waveguide, then you know what was the field propagating inside the waveguide. Let's say it's a rectangular waveguide. Dominant mode which is propagating in the rectangular waveguide is T10 mode. So you know the field in the aperture beforehand, and what we want to do is we want to find radiation from this open-ended waveguide or any kind of structures we have shown in the previous slide. So the first thing is you find the equivalent currents from the aperture fields. Aperture fields are electric field is EA, magnetic field is HA. So from there you can find the current density as n cross H and magnetic current density as minus n cross E. So that is the equivalent source from the aperture fields. This HA and EA are the aperture fields, and this is the equivalent electric current density and magnetic current density. So now once I have the electric current density, then I can find out the magnetic vector potential from this standard relation here. So this integration is over the aperture SA. So you understand what is ds dash and SA from the previous figure. This is the SA, surface of the aperture. ds dash is any small surface element you are taking, so ds dash is the area for that. So r and r dash is clear. R is the distance of the origin to the observation point. R dash is the distance of the source to the origin. So let us find what is the electric current density. Electric current density is N cross H. So now, since our aperture was confined in the xy plane, let us assume that magnetic field has two components. One is x component, one is y component. And normal to the xy plane is the z axis, so z hat. So you do cross product of z hat with the magnetic field intensity, you will get two components of the electric current density, x component and y component. X component is minus HAY and y component is HAX. So now we have the electric current density, then we can easily find the magnetic vector potential. Just replace electric current density in the previous expression by the new expression we have from the aperture fields, and we can find out the magnetic vector potential. And as you know that in the far field, r minus r dash would be equal to r. This is a very small number. This vector is very small comparison to the observation point, which is in a very far away distance from the antenna. In that case, you can neglect this for the amplitude term. But for the phase term, since you know that phase change from 0 to 2 pi, you cannot neglect it. We need to take some components which has contribution from r dash also. So r minus r dash is basically distance between the source and observation point. Observation point is as x, y, z, and the source point is in the xy plane. It will have only x dash and y dash. So you can find out the distance between the source and observation point is square root of x minus x dash whole square plus y minus y dash whole square plus z square. So now you can just expand this a minus b whole square, a minus b whole square, rearrange the term. Then what you have is, what is x dash square, y dash square, z dash square. Here z dash is 0, so x dash square plus y dash square. So x dash square, y dash square is here. What is x square plus y square, z square? That is r square. So r square minus 2x, x dash minus 2y, y dash plus this term here. So this is the expansion of this term here, a minus b whole square, a minus b whole square. You combine the terms x square plus y square plus z square, you get r square. So this is the expression you have for the distance between the source and observation point. We will try to analyze this for the far field. So now this term I want to analyze it for the far field, so I take a r command from here. When I take r command from here, this is the expression you have here, and this can be done binomial expansion. You will have many terms here. Let us take the first and second terms and neglect the higher order terms. So the first term will be obviously 1, second term will be x minus x dash by r square, y minus y dash by r square, x dash square plus y dash square by 2r. This is the second term. When you multiply by r, then this r square term will become r here. This one will become r here. So when you just consider the first and second term in the binomial expression and the expansion and neglect the higher order terms, this is the expression you have here. And moreover, in the far fields, you will see that even this term can be neglected. So when you consider far field of the antenna, even this fourth term can be neglected. In that case, we'll just have r minus x dash by r minus y minus dash minus y dash divided by r for the far fields. In the far fields, you can neglect this fourth term, and we'll try to see how we can neglect this fourth term. So you know that in the far field of the antenna, when you measure the phase, the error by approximating the spherical wavefront to a plane wavefront, the error should be pi by 8, less than or equal to pi by 8. So when I neglect this fourth term, how much is the phase error? Phase error will be beta times this term here, this fourth term here. So beta times x dash square plus y dash square divided by 2 r ff, ff for the far field. So this condition must be satisfied for the far field. When I assume the spherical wavefront to a plane wavefront, which is the wavefront for the far field, the error should be pi less than or equal to pi by 8. So beta times this term should be less than or equal to pi by 8. So in that case, beta is what, 2 pi by lambda. So this term here, x dash square plus y dash square by 2 rff, should be less than or equal to lambda by 16. So phase is the electrical length and the physical length should be half of that. So lambda by 16 here. So in that case, look at this diagram here. This diagram here, what you can observe is this is the distance of the source from the origin, which is r dash, and now this is lying in the xy plane. So r dash can be represented as square root of x dash square plus y dash square. So we replace r dash as square root of x square plus y dash square, and you know what is the range of value for this r dash. R dash can have value from 0 to d by 2. So r dash is square root of x dash square plus y dash square, and r dash can take value because this is the whole aperture here. At this point r dash will be 0. At this point it keeps on increasing. Maximum it can have is d by 2. So r dash can have range of value from 0 to d by 2. So r dash is bounded by d by 2. This is the dimension of this aperture here. So r dash is equal to square root of x dash square plus y dash square less than or equal to d by 2. You substitute it here in this expression. You put the maximum value of x dash square plus y dash square, that is d square by 4. So finally what you have is d square by 8 rff is less than lambda by 16. Then what you see is that the distance of the far field would be 2d square by lambda. D is the maximum dimension of the antenna. So this is giving you the far field of the antenna. When you move a distance of 2d square by lambda from the antenna, you are in the far field of the antenna. We are getting the exact relation we have discussed in one of the previous classes. How do you find the far field of the antenna? So far field of the antenna can be found out from this. When we neglect this last term here, how much is the change in the error in the phase? Error in the phase is pi by 8 less than or equal to pi by 8. In that case, distance rff should be 2d square by lambda. So now the phase term exponential minus j beta r minus r dash can be replaced by exponential minus j beta r minus x dash by r minus y minus dash y dash divided by r. The next order term we can neglect it because we are in the far field. Amplitude can be replaced by r. So this is what we have for the exponential minus j beta r minus r dash divided by r minus r dash. This is the expression you can use in the far field of the antenna. You also know that what's the relation between x and r? X is r sin theta cos phi. So x by r will be sin theta cos phi. Similarly, beta x is what? Beta times sin theta cos phi, that is beta x by beta is also sin theta cos phi. Similarly, y by r, beta y by beta is equal to sin theta sin phi. So in that case, you can replace the previous expression here. What this expression here, this exponential minus j beta r term is here, first term here. Second term is exponential j. You can replace this x dash by r as exponential j beta x dash, and you can replace this third term by exponential j beta y dash. So the final expression you have for the exponential minus j beta r minus r dash divided by r minus r dash as simply exponential minus j beta r plus exponential then exponential j beta x dash into exponential j beta y dash divided by r. So this is the far field approximation of this exponential term and the 1 by r minus r dash term here. You replace that in the previous expression for the magnetic vector potential. You can take out common exponential minus j beta r. Then finally what you have here inside the integration, this is what we need to look at it. So look at this expression, what you have in the inside the integration. What does it look like? This looks like your Fourier transform. So now what you are observing is that when I want to find the magnetic vector potential, I can find out magnetic vector potential as mu times exponential minus j beta r by 4 pi r minus Fourier transform of the aperture field in the y direction x hat plus aperture field Fourier transform of the 2D Fourier transform of the aperture field in the x component y hat. So basically this is a very profound result, very useful result. What we are observing is that when I want to find the magnetic field or magnetic vector potential here, from there we can find the magnetic field later on. When I want to find the magnetic vector potential, all I need to do is I need to know the 2D Fourier transform of the aperture field. So once I know the 2D Fourier transform of the aperture fields, then I can easily find out what is magnetic vector potential. Once I have magnetic vector potential in the far field, I can easily find out electric field and magnetic field. They are directly related. We'll discuss that in the following slides. So what we observe is I want to find magnetic vector potential. All I need is to have this term, and I need to find the 2D Fourier transform of the aperture field. Once I know the 2D Fourier transform of the aperture field, I will be able to find out magnetic vector potential, and electric field and magnetic field can be later find out. So the radiation pattern of the antenna would be the main parameter which will change the radiation pattern for the antenna would be the 2D Fourier transform of the aperture field. So this is a very profound effect. So when you want to find the fields radiated from a aperture antenna, you need to do Fourier transform of the aperture fields. Similarly, you can also do it for electric vector potential. Electric vector potential expression is this: epsilon by 4 pi integration over the aperture. This is the magnetic current density exponential minus j beta r minus r ds divided by r minus r ds. ds. We already know what is the expression for this in the far field, and following the same technique we have mentioned in the previous slide, we can also find the electric vector potential by taking the 2D Fourier transform of the aperture electric field. So this is the expression for the electric vector potential in the far field of the antenna, and it is directly dependent on the 2D Fourier transform of the aperture electric field. So once you know the 2D Fourier transform of the aperture electric field and magnetic field, you can find out the radiation pattern of the antenna easily. So Fourier transform plays a significant role in the finding the fields of the aperture antennas. Note that we have a magnetic sign, negative sign here is due to we define magnetic current density as minus n cross Ea, but electric current density is n cross Ica. So you have a negative sign here, that's why we have a minus sign here. And here, when I want to find the fields, I always consider a sphere and different locations, different directions, different theta and phi. I find out the fields. So spherical coordinate is the coordinate which should be used for finding the fields. So we need to do a coordinate transformation, because what we see here, our fields are in the xy z coordinate system. I want to transfer it into the spherical coordinate system. That you have already done many times now. So this is the coordinate transformation from the Cartesian coordinate to spherical coordinates. Let's say you want to transform ax, ay, az to ar, a theta, a phi. You multiply by this coordinate transformation matrix. We have discussed how to get this matrix also in one of the previous classes. Similarly, if you want to find fr, f theta, f phi from fx, fy, fz, you multiply by this coordinate transformation matrix. So now in the far field of the antenna, we will not have any components ar or fr, they are 0. So for the equivalent source in the xy plane, what happens to az and fz? So source is in the xy plane. So basically you know that potential, electric vector potential and magnetic vector potential follows the direction of the magnetic current density and electric current density. Now our electric current density and magnetic current density is confined in the xy plane. So obviously we will not have Az which is equal to Fz equal to, it should be 0, because our electric current density and magnetic current density is confined in xy plane. So electric vector potential and magnetic vector potential will also be confined in xy plane. It will not have any z component. So this term is also 0. So now you do coordinate transformation. If I want to find a theta, then I can simply find out as this here. this term mu exponential minus j beta r by 4 pi r minus HAY tilde here means is Fourier transform, 2D Fourier transform, cos theta cos phi plus ICAX tilde here means 2D Fourier transform. Similarly, Fy also you can find out ICAY sin phi tilde ICAY tilde sin phi plus ICAX tilde cos phi. So we have the expression for A theta and A phi. From the aperture fields, magnetic fields, by taking the 2D Fourier transform, you can find out A theta and A phi. Similarly, you can also find out F theta and F phi from the 2D Fourier transform of the aperture electric field. Tilde here means 2D Fourier transform. These expressions are obtained after applying the coordinate transformation from the Cartesian coordinates to spherical coordinates. So you have electric fields, and basically what you want to find is the electric field and magnetic field. Magnetic vector potential and electric vector potential is find out first so that we can easily find the electric field and magnetic field. We have already discussed about that, why we find first electric vector potential and magnetic vector potential and find the fields. It's easier for us. So now the electric field in the far field will have contribution from the magnetic vector potential and electric vector potential. So we'll have two components, one from A and one from F. So now what is the electric field in the far field contribution from the A vector? That will be simply minus j omega A theta theta hat minus j omega A phi phi hat, because you know that electric field was what? Minus negative gradient of electric potential minus dou A by dou T. What is dou A by dou T in the far field? Dou A by dou T is basically when you have time harmonic fields, dou by dou T will be replaced by j omega. In that case, the first contribution from the negative gradient of electric potential doesn't have any contribution in the far field of the antenna. So minus gradient of electric potential is 0 in the far field of the antenna, negligible. The only contribution will be minus dou A by dou T. Minus dou A by dou T in the time harmonic case is minus j omega A, and A has only theta and phi components. So what you have is EFF contribution from magnetic vector potential would be minus j omega A theta theta hat minus j omega A phi phi hat. Similarly, you can also find out the electric field in the far field due to the electric vector potential. Contribution can be found out as eta times magnetic vector potential in the far field contribution from the F vector cross product with R. So once you have the magnetic field, you can find out electric field as eta times cross product of the magnetic field with the radial unit vector. So that's a standard thing in the far field of the antenna. The ratio of the electric field and magnetic field is eta, and magnetic field is perpendicular to the electric field, and it's also perpendicular to the direction of the pointing vector, which is along the radial direction. So how do I find this magnetic field in the far field due to contribution from F vector? Same thing, you can find out IFF contribution from F vector is simply minus j omega F theta theta hat minus j omega F phi phi hat, just like what you have done for the electric field contribution from A. Magnetic field contribution from F vector will be minus j omega F theta theta hat minus j omega F phi phi hat. But what we are interested is in the electric field. So you can use this relation to find the electric field, and you do the cross product. Finally, electric field will have two components, theta and phi, and you can find out what is the theta and phi component from this relation you have here. So you can write down the expression for electric field in the far field. Theta component is minus j omega A theta minus j omega eta F phi. Electric field in the far field phi component is minus j omega A phi plus j omega eta F theta. So now you have this expression. Now you know what is the expression for A theta and A phi. We have already derived this here. A theta is this, A phi is this, A theta is this, A phi is this, F theta is this, F phi is this. We have already derived it. You plug it, the values of A theta and F phi, A phi and F theta in this expression, then you will get the electric field in the far field theta component, which expression is this, and electric field in the far field theta component, you can even simplify it. Just plug it in here. This expression you can further simplify it. That simplification is done here. What you have is omega mu exponential minus j beta r by 4 pi r. You multiply by beta in the numerator and denominator. Then what do you have? What is omega mu by beta? Omega mu by beta is eta. So the expression you have is j eta beta exponential minus j beta r by 4 pi r. So this term can be simplified like that. This term also you can simplify it. What is j omega eta epsilon exponential minus j beta r by 4 pi r? You can further simplify it. What is eta here? Eta is omega mu by beta. So now what you have here is omega square mu epsilon. Omega square mu epsilon is what? Beta square. So this beta and beta square cancels out, j beta exponential minus j beta r divided by 4 pi r. So you replace the first term here by this. So we need to replace this term here by the new derived terms you have here and here. So when you do that, you can write a more compact expression for the electric field in the far field of the antenna. Theta components j beta exponential minus j beta r divided by 4 pi r. Eta times this term here inside the first bracket, then plus this term here. So this term is contribution from the aperture magnetic field, this term is contribution from the aperture electric field. Similarly, you can also find out EFF, electric field in the far field phi component is j beta exponential minus j beta r by 4 pi r minus eta times this term here plus this term here. This term is the contribution from the aperture magnetic field, this term is contribution from the aperture electric field. So we'll call this as 24.1 and 24.2 equation. We'll be using these two equations for finding the fields in the far field of an aperture antenna. We'll consider different types of aperture antenna and try to find the fields in the far field of the aperture antennas. For that, we need to know these two equations. We have the expression, this is a general expression for electric field in the far field of a aperture antenna based on the aperture magnetic field and electric field. So for different kind of aperture antenna, this aperture electric field and magnetic field is going to change, but the expression for the far field of the antenna is not going to change. This is a general expression, so we'll use this general expression. This is lecture 24, so I'm calling it equation 1 and equation 2 of lecture 24, and we are going to use this for finding the electric field in the far field of any kind of aperture antennas. We'll be discussing from now onwards. So what's the procedure for finding the electric field and electric field in the far field of an aperture antenna? All you need to do is find out the 2D Fourier transform of the aperture magnetic field and electric field and put it here. So the aperture electric field and magnetic field for different aperture antenna is going to change. Because of that, when you take the Fourier transform, it's going to be different for different antennas. So the radiation pattern will be different for different antennas, because this term here is going to change for different kinds of aperture antennas, and this term is these two terms are actually you get it from the 2D Fourier transform of the aperture magnetic field. These two terms are from the 2D Fourier transform of the aperture electric field. So Fourier transform plays a significant role in analyzing the radiation pattern of aperture antennas. Once you know the aperture fields, take the Fourier transform, plug in those values in this expression, equation 24.1 and 24.2, 24.1 and 24.2, you will be able to get the aperture fields. That is the exercise we are going to do for the following classes. Thank you.